All right, section 3.4 in our chapter talks about other types of unit for solution concentration. So we have already mentioned moles of solute per liters of solution as a way to express the relationship between solute and solution. Percent is grams of solute per 100 grams of solution. So to calculate that, you would take grams of solute, divide by grams of solution, and then multiply by 100 and use the percent as our unit there. You can also do the percent in terms of volume, so milliliters of solute per milliliters of solution. This is very helpful when you have a liquid solute. And then you would multiply that by 100 in order to express that as a percent. You can sometimes have mass volume percent. This is helpful when you have sugar solutions, some glucose solutions, IV and stuff. You want to know how many grams of solute you have in there, but you don't want to have to measure the grams of solution or weigh it out. You want to just use a syringe or something that's going to measure volume. So knowing the grams per milliliter or grams per 100 milliliter actually is helpful. So we would divide grams of solute per milliliters of solution by 1, then multiply by 100%. So percent is kind of something that means per 100. And sometimes we have much lower concentrations than that. Hopefully, if you are talking about things that are polluted or contaminated, you would have a lot less than a percent of contamination. You might have a part per million of contamination. And so instead of a part per 100 where you multiply by 100, to get part per million, you would multiply by 1,000,000, which is 10 to the 6th. Some levels of contamination might be even lower, parts per billion. And so to get parts per billion, you multiply by 1,000,000,000, which is 10 to the 9th. So this is in order to calculate concentration in parts per million and parts per billion rather than percent, which is parts per 100. You would take the grams of solute divided by grams of solution and then either multiply it by 1,000,000 or 1,000,000,000 to get these solution concentration units. So this is one type of problem where you have to calculate what the concentration is. And that's where these formulas could be useful. Another thing that you might be asked to do is to use the concentration as a conversion factor. And so you should know what the concentration means. We did a few of these before where we would have molarity concentrations. When we used these as conversion factors, we used the knowledge that 1 mole or 1.75 molar means 1.75 moles of solute in every liter of solution. So percent, especially percent by mass, so mass percent, 3.5 mass percent of sodium chloride means per 100. So every 100 grams of your mixture, because we're talking about mass, has 3.5 grams of your solute in it. So that means that there's 3.5 grams of sodium chloride in every 100 grams of solution. Volume percent is similar, it's just milliliters per 100 milliliters. So we have 11.7 milliliters ethanol per 100 milliliters of solution. And then if we had mass to volume, then that would be grams per 100 milliliters. So 8.5% mass to volume is 8.5 grams per 100 milliliters of solution. So this is a very important step to be able to take the concentration that's given to you and express it as a relationship that you can use as a conversion factor. All right, let's keep going with ppm. What does ppm mean? 4.2 ppm, parts per million. That means there's 4.2 grams per million grams, parts per million. So we have grams per million gram. 4.2 grams of lead in every million grams of solution. So then these are just other ways to express that. You could divide both sides by 10 to the 6th, and you would get 4.2 times 10 to the negative 6 grams per gram of solution. And 10 to the negative 6 grams happens to be a microgram. So another way to look at this is that we're saying that there's 4.2 micrograms of lead per every gram of solution. ppb is very similar. there's 2.7 grams per billion grams of solution. That's what ppb means. So again, we can express it like this, grams per billion grams. Or you could divide both sides of this equation by 10 to the 9th and know that every gram of solution is going to have 2.7 billionths of a gram of arsenic, or 2.7 nanograms of arsenic. So this is a second type of problem that you can find that has to do with solution concentration, one where you have to use one of these solution concentrations to do a conversion. And so you would need to know the relationship. So a third type of problem we are going to see at the end of the section is a problem where we take concentration with one unit and convert it, and still convert it to the concentration, so we're keeping the concentration, but we're converting it to other units. So for example, we might take molarity concentration and convert it to mass percent concentration. So this first problem here is one where you're trying to calculate the concentration. So that's one of the types of problems that we see. Mass percent concentration is the grams of solute per gram of solution times 100%. So we are given all of the numbers that we need to do this calculation. We're given grams of solute and we're given grams of solution, and then we can get a fraction from that and turn it into a percent. This next problem is really helpful for lab 3, because for lab 3, you're not given the information that you have this many grams of sodium chloride and you're making this many grams of solution. What you end up with is you go to lab and you measure these masses, and then you have to figure out what the mass of sodium chloride is and what the mass of solution is from what you've measured in lab. And then you can apply this formula and figure out the mass percent. And hopefully it makes sense that to figure out the mass of sodium chloride, we can take the mass of the beaker and sodium chloride together, subtract the mass of the beaker, and that would give us the mass of sodium chloride. When we do this, we get 4.985 grams of sodium chloride. Now we need to find the mass of the solution. The solution is the mixture. Remember, solute is sodium chloride, solvent is water. So the solution here means the sodium chloride and the water together. So we want to know the mass of the sodium chloride and the water together. So to do that, we could take the mass of the beaker with the sodium chloride and the water together in it, so the beaker and the solution, subtract the mass of the beaker, and we get the mass of just the solution. And this comes out to be 108.902 minus 83.402, which is 25.500 grams. So it's important to keep 3 past the decimal. Whenever you're working with our lab balances, that's how far you know your masses. So now that we have figured out the mass of our solute, 4.985 grams, we can divide that by the mass of the solution, which is 25.500 grams, and then express that fraction as a percent, and we are getting 19.55% sodium chloride by mass. So you're going to be doing this for all of the solutions that you make in lab 3. So this problem is a little bit less involved than the one where you have a chart and different masses and you have to figure out what the solute mass and what the solution mass is, but you do have to pay attention. So in this particular problem, you weighed your water, which is your solvent, and then you weighed your potassium bromide, which is your solute. You did not actually weigh the solution, but we can figure out the mass of the solution because the solution is the water and the potassium bromide together. And so if we added 45.73 grams of water to 0.82 grams of potassium bromide, then it's reasonable to think that we have 46.55 grams of solution. So then we could calculate our mass percent concentration by dividing the 0.82 gram solute by the 46.55 grams of solution, and then converting that fraction to a percent, which gives us 1.8% potassium bromide solution by mass. Okay, so this problem, we are calculating the volume percent concentration. So instead of grams over grams, we have milliliter solute over milliliter solution, and then that fraction converted into a percent. So our solute is ethanol. Here's our volume of ethanol over the milliliters of solution. And that brings us to 39.5% ethanol by volume, or 39.5 volume percent. If we have mass volume percent, the solute is measured in grams, the solution in volume, or milliliters, and then that fraction turned into a percent. And this comes out to be 13.93% glucose. So another way you can express the type of percent, mass to volume, you can just sort of specify M over V in parentheses next to the percent. So this is the mass volume percent. You could even put that here if you want to put that it's volume percent. You could put V over V. So let's do some problems where we are using these concentrations to convert either from solute to solution or from solution to solute. So this is asking about the solution above. The solution above is 13.93% glucose, and that's a mass volume percent. So what that means is that there are 13.93 grams of glucose for every 100 milliliters of solution. So this is the relationship that we can use to convert from grams to milliliters. If we want 7.86 grams of glucose, we'll go ahead and put the 13.93 grams of glucose in the denominator so that it cancels. And it turns out we would need 56.4 milliliters of this solution to get the 7.86 grams of glucose. So 42.0 volume percent solution, or percent by volume, means that there are 42.0 milliliters of methanol, the solute, in 100 milliliters of the mixture or the solution. What we are starting with here is 632.5 milliliters of the solution. It's important to know that you're starting with the milliliters of the solution, not methanol. And when you write the conversion factor, you might want to be a little bit more specific instead of just writing milliliters over milliliters, because milliliters are going to cancel either way. But if you write that this is milliliters of solution on the bottom, then you know that you're canceling milliliters of solution, and you'll end up with milliliters of methanol. And so we would have 266 milliliters of methanol in this 632.5 milliliters of solution. Another thing that could be helpful is to make predictions. So if we had done this with these problems, we would know that, to get 7.86 grams, we need a larger number of milliliters. We can't just have 7.86 milliliters or fewer milliliters. It has to be a larger number. And so then we are more confident when we get that larger number. For this one, if this is the mixture, 632.5 milliliters, the amount of methanol in that mixture has to be smaller than 632.5 milliliters. And so then we can be more confident when it is. Okay, so here, for example, let's make a little prediction before we try the problem this time. We want to get 45.0 milliliters of alcohol. And we are getting that alcohol from some wine, and the wine is 9.87% by volume alcohol. And so the volume of wine that you need to get that much alcohol has to be more than 45 milliliters. You're not going to be able to have 45 milliliters of alcohol if you only pour out 25 milliliters of wine. So we're going to have to pour out more than 45 milliliters of wine in order to get 45 milliliters of alcohol. I'm going to go ahead and do this up here so people can see it better. Let's write our relationship. What does 9.87 volume percent mean? It means that there are 9.87 milliliters of alcohol in every 100 milliliters of your solution, which is wine in this case. We're going to go ahead and write the conversion factor this way with alcohol on the bottom because we want to cancel alcohol and have our answer be a volume of wine. And this ends up being 456 milliliters of wine needed, and that does make sense. It is more than 45 milliliters of wine, and so this gives us more confidence in our answer. All right, so these problems we are back to calculating concentration, but these are ppm and ppb concentration. So we have that added wrinkle of a power of 10 that confuses people sometimes, so let's make sure that we can do these. All right, so we want to have our grams of lead over our grams of solution. So the wastewater, the contaminated water, is the solution. It's the mixture of water with some lead in it. So that's our solution. We have that many grams of solution, 950,000 grams. The grams of lead isn't given to us directly. We have 4.6 milligrams of lead. So that is 4.6 times 10 to the negative 3 grams of lead. Let's go ahead and put that. So I just put this intermediate math, converting the denominator to scientific notation if some people find it easier to see that way. But this should come out to be 4.8 times 10 to the negative 3 ppm of lead, or you can also write it in regular notation, 0.0048 ppm of lead. So for ppb, it's kind of similar. It's just that we need a billion ppb. There's a billion parts in a billion, so we need 10 to the 9 here. So this time we're given our grams of solute. There's 0.000052 grams of antimony. We have 750 kilograms of solution, which is 750. A kilogram is 10 to the 3 grams, so it's actually 750 times 10 to the 3 grams of solution, which can also be written 7.5 times 10 to the 5 grams. So again, I just rewrote this, grouping all of the powers of 10. But this comes out to equal 6.9 times 10 to the negative 2 parts per billion antimony, or if you write it in regular notation, 0.069 ppb antimony. For this problem, we are not calculating the concentration. So we have the concentration already given to us, and we're going to use that relationship to do a conversion. So this 3,500 kilograms of water, this is the contaminated water, so this is the solution. So we are converting from 3,500 kilograms of the solution, the contaminated water, into the amount of lead, which is the solute. And the relationship that we have, the 65 ppm, that's a relationship. The 65 ppm means 65 parts per million. That's 65 grams of solute, lead, in every million grams of solution. So you can use the number 1 million if you want to. I just use scientific notation because it's easier for me. So starting with kilograms of solution, we can't use this conversion factor directly because it's a conversion factor that uses grams of solution. So we can convert this to grams, and we will have grams of solution at this point. Now we can use our concentration as a conversion factor, 65 grams of lead in every million grams of solution. So when I do that calculation and round down to 2 significant digits, I get 2.3 times 10 to the 2 grams of lead, or 230 grams of lead in this contaminated water sample. These last 3 problems are a type of problem where we're changing from one concentration to the other. So here's a list of different types of problems that we've been seeing. We've had some where we calculated the concentration, some where we used the concentration to convert between amount of solute and amount of solution. And now these last 3 are ones where we have the concentration with 1 unit and we want to express the concentration but with another unit. So we are given the concentration in mass volume percent. We are told it's 17.5 mass volume percent lithium bromide. That means there are 17.5 grams of lithium bromide in every 100 milliliters of solution. And we want to calculate the molarity concentration, which would give the concentration in moles of lithium bromide per liter of solution. So we are going to have to convert grams to moles for lithium bromide and milliliters to liters for solution. It doesn't matter what order you do this in, so let's go ahead and change the milliliters to liters first, using whatever conversion factor you prefer, but a lot of people find it easy to use 1,000 milliliters in a liter. To do the next step, you need the molar mass of lithium bromide, which if you use the periodic table you can find is 86.84 grams per mole. So if you do this, the milliliters cancel and the grams of lithium bromide cancel, and we are left with moles of lithium bromide per liter, which is what we want. And this comes out to be 2.02 moles of lithium bromide per liter of solution, which can also be written 2.02 molar solution of lithium bromide. Okay, this next one we are given the molarity concentration. So we know that there are 4.81 moles of potassium hydroxide in a liter of solution. And we want the mass percent concentration. So we want to know how many grams of potassium hydroxide are in 100 grams of solution. And it's probably easier to find the grams of potassium hydroxide per gram of solution and then multiply that by 100%. That's how we normally calculate the mass percent. So when we multiply by 100%, we get 100 grams per 100 grams of solution, and we just express that as a percent. So let's try and get the grams of potassium hydroxide per grams of solution and then multiply that by 100 to get the mass percent. So this is what we really want, but the way to get there is to get to grams per gram and then multiply that by 100%. So converting moles of potassium hydroxide to grams needs the molar mass of potassium hydroxide, which is 56.11 grams per mole. So multiplying this 4.81 moles KOH per liter by the molar mass, 56.11 grams of potassium hydroxide per mole of potassium hydroxide, that would convert the potassium hydroxide to grams. Now we need the solution to be in grams of solution, and we have liters of solution. So we can convert the liters to milliliters. Now we need to convert milliliters of solution to grams of solution, and for that we need to use the density that we were given. So a milliliter of solution is 1.25 grams of solution. So now we've canceled moles of potassium hydroxide, we've canceled liters, we've canceled milliliters. So we have grams of solution in the denominator and grams of KOH in the numerator, and that's what we are trying to get. That comes out to be 0.216 grams of potassium hydroxide per gram of solution. And then if we multiply that by 100%, if that's how many grams are in a gram of solution, then if we multiply that by 100, we'll get how many grams are in 100 grams of solution, which is our mass percent. So this comes out to be 21.6 mass percent. So for this next problem, we are again converting from one type of concentration to another. We are converting from mass percent into molarity. So we're starting with 22.0 grams of methanol per 100 grams of solution. That's what the mass percent means. And we want to know how many moles of methanol are in each liter of solution. So we are going to need the molar mass of methanol, which I've calculated here, and we are also given the density of the solution. So first let's use the molar mass to convert the grams of methanol into moles of methanol. So now we have moles of methanol per gram of solution. We need to convert from grams to milliliters so we can use the density. So if we use the density here, we can cancel the grams of solution. And at this point we have moles of methanol per milliliter of solution. We want this to be liters. So that is a metric conversion. And that cancels milliliters. And that gives us 6.61 moles of methanol per liter of solution, which can also be written 6.61 molar methanol solution.